That's right. I think we talked about yeah, he's a spy. We talked about this previously. So I don't know. Let me give a speech. I know you could too. But it's really very interesting, actually. It's good to know. And it's the same sort of idea. The point being that if you have this kind of an argument, namely that a wave superposes and can form like a particle-like thing, the synthesis of shapes is a question of adding sine waves. Now, AM actually stands for amplitude modulation. And FM stands for frequency modulation. Now, it is true they're on different bands. This one happens to be, if you look up on your radio, it'll be like 100 kc, or kilohertz. And this one will be like 100 megahertz frequency. That's what you said, which is quite right. They're in different frequency ranges. That's true. But the fun thing has to do with, and that's what it says on your dial. If you actually look on a radio dial, it'll actually say 98.6 megahertz, which is million cycles per second, which is the, and this one will say KGO 96 kilocycles on your radio dial. Sound like a radio announcer? 96.6 on your radio dial. Okay, KGO. Okay, so, but the real difference is that that tells you what they're doing is they're sending out a carrier frequency of that amount of each station. Each station has its own what's called carrier frequency. And that's the one they announce. That's that. But that alone doesn't transmit much information. It just says, I'm here. It's just one signal, right? I'm here. But it doesn't tell you, it doesn't have much more information than that. Suppose I want to say loud signal, soft signal, loud signal, soft signal, right? Well, you have to put that information on this carrier. So amplitude, you remember what amplitude? Amplitude is the height of the wave, right? From peak to middle, that's the amplitude of the wave. The frequency is how rapidly it goes. So the amplitude modulation is, I put the information on the amplitude of the wave. So I have my carrier, let's say 100 kilocycles. Let's do AM rate. AM's amplitude. So I have 100 kilohertz amplitude wave, frequency. But then I want to put information on it. So I say, get this, loud wave, soft wave, loud wave, but I keep the frequency the same. So that's the information, loud, soft. Also, within that, I put on the frequency. Like, since it's 100 kilocycles, I can put on there, that's a lot of cycles in a second, I can put on variations like frequency on that amplitude. So I'm saying, high pitch, low. I keep the frequency the same, but I vary the amplitude according to the frequency of my voice. Can you see how you would do that? The frequency of your voice is superposed on this very high, because our voices only go to about 10, 100 kilocycles, no, 10 kilocycles, or 20 maybe, 20, yeah. So if it's 20 kilocycles, I have 100 in here, I can afford to put 20 kilocycle variations on that. So there might be 20 kilohertz variations on the 100 kilocycles, plus amplitude. So I can tell you the pitch that I want, and I can tell you how loud I want it. So when the orchestra crescendos, you get a big signal, and you can tell that it's the violins, because that's the frequency mixture. Get that point? Yes, sir. It's recording on this carrier the frequency of your voice by the frequency with which the amplitude goes up and down. In other words, I have an awful lot of cycles, but my voice could be very slow, is relatively slowly varying. So I get a thing like this telling me what my voice frequency is. And how loud my voice is depends on the size of the wave. In other words, I could say the same thing, here's my carrier. I could say the same thing, but then I would have, with the same pitch, the wave would look like that. See, it's the same frequency of my voice, but the amplitude is now much lower. So that tells the radio how loud I spoke. This tells the frequency I spoke. See, the amplitude of this. So it's all written down on the amplitude of the wave. Both my frequency, if I go up in frequency, here's my carrier. If I go up in frequency, I'm making more rapid vibrations, like that. And that would be a pretty loud one, because it's that loud. On the other hand, I could go, here's my carrier. And if I want to make a real small voice, but way high, I go very high frequency, but I make the amplitude real low. And so that's what the signal would look like, with a high frequency and a low amplitude, low loudness. So this is the loudness, and this is the pitch. And that's pretty much all I need to know, how loud and what frequency. And what's all encoded on the amplitude of the carrier. And that's called, and this kind of writing on things called modulating. You modulate the carrier with the signal you're trying to send. Okay, more or less. I think this is interesting. I mean, now, what this has to do with Heisenberg uncertainty is that you start out with a carrier, let's say that's 100 kilohertz, but when you start writing stuff on it, you write your voice with other frequencies nearby. So like you need like 20 kilohertz for your voice to be written on here. So actually a radio station is allotted a certain space, including its carrier, plus how much space it needs to carry the signal on it, like the 20 kilohertz. So you're assigned a band. Each station is assigned a band in a certain geographical location, because you don't want the next radio station to be sending signals into you. And you tune your radio with an inductor and a capacitor. By tuning this, you tune it to this particular station with its range, and you can pick it up. And of course, so this tells you the frequency that you're sending, and by the amount of it, it tells you the amplitude. So you can vary the amplitude of that. This is sometimes called a sideband, which is on the sides of your carrier. So this is your carrier, and it's again the same story, wherein I'm trying to locate, I'm fooling around with the frequencies and wavelengths of my waves to create shapes. I'm trying to create this shape by adding the carrier frequency together with the voice frequency and amplitude. Get that? I think it's interesting. Now, the other thing is frequency modulation. See, the wave has various characteristics. So you can write stuff on the amplitude, but you can also write the information on the frequency of the wave. So that is done differently. The frequency, of course, is the rate at which the wave repeats itself, like the time between peaks. And the frequency is 1 over that time, how often it cycles back and forth. But you can write the information by varying the frequency. So, for example, let's say I wanted to go to a high pitch. Well, normally my frequency might be a certain amount. But if I want to write on the fact that I want to go higher and higher, I can maybe make the frequency higher. And then if I go lower, lower, higher, higher, lower, lower. See, so I can, and this tells me this is a high pitch, it's a low pitch, high pitch, low pitch. So I can write the information on the frequency. So that's another way of doing it. How would you do the amplitude? Well, that's a good question. Not quite sure how you write the amplitude here. Maybe somebody come up with that idea. But the beauty part of this one is that why FM is sometimes better than AM is because when you want to have a soft sound with AM, you have to make the amplitude less. And then if there's noise or static in the radio, like atmospheric static, it may swamp this signal. See, but with FM, you don't fool around apparently with the amplitude. You just write everything on the frequency, so you can have a nice big amplitude, even for apparently soft sounds or loud sounds. So that's, again, so it's really what the words say. You modulate in order to put information on this signal. In the case you have a wave and you want to amplitude modulate, that's what you do. You vary the amplitude and write the information on the amplitude of that carrier. On the frequency modulation, you change the frequency in order to do this. Okay? You happy you came? At least you know when you look at a radio what you're looking at. It's a good thing. Okay. I don't know if we know any more about Mr. Heisenberg, but okay. How much time do we have? Zip. Very little. Okay. Any questions about that? It's more cultural information, frankly. But I think it does all tie together, and it's all properties of the waves. I think I'm through with this. And you see how, in my notes, I show you how to go, in fact, I go through the steps, namely using one pulse, one wave to try to simulate that, and then 2 and 3 and 4 and so on, and how you can just build up the shape by the superposition of many, many waves. Okay, that's fine. Now, I want to say a few more things about this. We had quite a discussion in class today, in the office hour actually, about where bands come from, the band structure of solids, and the point is that what we simply are doing is we're taking the energy levels of atoms, and when we bring the atoms together, close together, their wave functions overlap, and they spread into bands of energies. I tried to show you that last time by taking just 2 wells and bringing them close together, and the wave functions tunnel from one well to the other. Think of the wells as atoms. And so then the question is, when do you get conductivity? You get conductivity when you have a band that has electrons in it, but the band is not full. If the band has states that the electrons can pick up energy in that band, then the electron can move. It can move from one energy state to another within the band. But there are gaps between the band. And this sorts materials into various types. Namely, if, for example, you start out with electrons in an energy level in a material, and it spreads into a band, if there are no electrons in the next higher band, and there's a large gap between here, this we would call an insulator, because the electric charges, if you put a field on this, the electrons can't move within this band. They can't pick up energy because they're up to the highest level in this particular band. And these gaps, if this gap is, here's where temperature comes in, thermal issues. See, the gaps can be of the order of electron volts, whereas the room temperature, we've said various times, the energy is about a 40th of an electron volt. So the electrons can be kicked by that 40th of an electron volt to higher energy states, and that's kind of like excitation. So if you have this full band, which we sometimes call the valence band, and you have a 40th of an electron volt is kT, Boltzmann factor T. In other words, room temperature just can push things up ever so little, and you need, like, let's say 5 electron volts up here. A 40th is around 200 times or 20 times too small. No, it's worse than that. It's 200 times too small. You get this sort of exponential factor that you need 5 electron volts, and kT is a 40th, say, so you get e to the minus 5 over kT is a 40th of an electron volt. And so then you get e to the minus 200, which is a very, very small number. In other words, it almost never happens that an electron gets enough energy from heat in the ordinary room temperature to find its way into this state from which it can then move. Think of this as a highway, and this is a full parking lot. And you need a certain amount of energy to get into the highway, and a 40th electron volt is not enough to get you into the highway. So this would be called an insulator because there are no free electrons. The number of free, that is free or in the conduction band, conduction electrons, is vanishingly small, 0. E to the minus 200 is nothing to speak of. It could happen that the energy gap is smaller. It depends on just what those original atomic energy levels were. In semiconductors, the gap is smaller. It's not as big as typically as 5 and 10 volts. It's maybe more like 1 or 2. It still is not enough, frankly. So we have a way of dealing with semiconductors to make them useful conductors. And then you have the case of metals, where the conduction band is either not full or it overlaps another band which is empty and so can carry carriers. Now, the greatest case of that is that the first row elements like lithium and sodium, where you see that they start out as, say, the 2s electron in, I guess it would be lithium. And when it forms a band, there's only 1 electron in a band that can hold 2 electrons. You see, because you could have electrons spin up and spin down, but there's only one electron. So the orbitals of this are the 1s for hydrogen and the 1s for helium. Then you have 2s, which would be lithium, and it has one electron, but it can hold two. See, there's an empty state here. So this electron is in a band that's not full. And so lithium is a very good conductor, but it's also extremely reactive. So if you put it in air, it'll catch fire. But it would make a good metal. And it is a metal in the liquid state, for example, because that electron is in a band that's not full. So let me see here. So this is another picture of that sort of thing, where if you have a large gap between places where the electrons occupy and where they can move freely, we call that an insulator because no electrons can thermally be excited from here to there, but from here to there. So I think insulators are nice, but a little bit boring, since they don't conduct very much, and that's more or less what we're interested in. But let's see what we say about them here. They have low conductivity because this number in the unfilled on the highway are very small. Because of this large energy gap, n is approximately 0 at room temperature. So sigma is 0 because n is 0. And the reason n is 0 is because you have this large gap, kT being small. And you get something like e to the minus, what do I get, 200 here. So it's a freeze-out issue. That the temperature is so low that all the electrons are frozen out here, and they can't jump across the gap. So it's the same reason why Planck's oscillators don't oscillate. But the more interesting case, let me show you very quickly, if I may, if you have patience. Now, even in a semiconductor, we speak of two different kinds of semiconductors, the intrinsic and extrinsic. Now, an intrinsic semiconductor it develops its bands from the atomic states. But the gap could be relatively small, perhaps, in which case there's enough thermal energy to excite a few electrons up into this conduction band, and you get a few electrons, if the gap is small enough. But the reason semiconductors are a big deal in industry is that we can artificially make them into good conductors, so-called extrinsic. By putting something extrinsic into the semiconductor, we can adjust its